You ever look at a math problem, see that big number with a little number kind of floating up next to it, and you're just like, what in the world is that? Well, today, we are going to crack that code. We're going to explore one of the most powerful and honestly one of the coolest shortcuts in all of math. Let's get into it.
So let's just jump right in with a classic example. 4 with a little 3 next to it. We say 4 cubed, or 4 to the third power. Now your first guess might be, oh, that's just 4 times 3. But nope, that's not it. This is actually a super compact code for something way more interesting. And to really get it, we need to take a quick step back to the basics of multiplication.
All right, section 1. From factors to repetition. To really understand what's happening with these powers and exponents, we've got to start from the ground up, with a concept you already know really well. Factors.
Let's start with an equation everybody knows. 2 times 8 equals 16. It looks super simple, I know, but the specific words we use to describe the parts of this equation are absolutely crucial for what's coming next. So, in this equation, those numbers we're multiplying, the 2 and the 8, they have a special name. They're called factors. You can think of them like the building blocks that come together to create the final product. In this case, 16. Simple enough, right? But this brings up a really interesting question. What happens when all the building blocks are exactly the same? For instance, we can also get to 16 by multiplying 4 by 4. See? In this case, our factors are identical. We're just repeating the same number. Now, writing out 4 times 4 is no big deal, but what if we need to repeat that number a whole bunch of times? And that brings us to section 2, the power, a shortcut. This is where that clever little math code comes into play. It's called a power, and it's just a brilliant way to handle this idea of repeated multiplication without getting a cramp in your hand.
I mean, can you imagine having to write this out every single time? 4 times 4 times 4 times 4 times 4. Ugh, it's so long, it's tedious, and it is incredibly easy to lose count. There's got to be a better way, right?
Of course there is. You know, mathematicians are all about finding efficient ways to do things, and they came up with a really elegant solution to represent this exact idea.
And there it is, 4 with a little 5, 4 to the 5th. Instead of writing out 5 different 4s, we just write it like this. We'd read this out loud as 4 to the 5th power, and it means the exact same thing as that super long string of multiplication we just looked at. Way cleaner, right? So when we talk about a power, we're really just talking about a number that's the result of multiplying equal factors together. That whole expression, 4 to the 5th, is the power. It's one neat, tidy package for what could be a really long calculation.
Okay, section 3, anatomy of a power. Now that we've seen this shortcut in action, let's pull it apart and learn the names for its different pieces. It's actually really simple.
As you can see right here, a power is made up of 2 key parts. You've got the base, and you've got the exponent. Each one has a very specific and very important job.
First, let's talk about the base. That's the big number on the bottom. I like to think of it as the star of the show. It's the number that's actually getting multiplied over and over again. So in our example, 4 to the 5th, the base is 4. And then you've got the exponent. That's the little number up top. And if the base is the star of the show, while the exponent is the director, its only job is to tell the base how many times to show up in the multiplication problem. So for 4 to the 5th, the exponent, 5, is just telling the base, 4, hey, I need you to multiply yourself 5 times. Section 4, putting it all together. Okay, so we have our 2 key players, the base and the exponent. Let's run through a few more examples just to see how they dance together and make sure this whole thing is crystal clear.
All right, let's just walk through this table together. First row, we've got 4 squared. The base is 4, the exponent is 2. So what does that mean? It just means 4 times 4, which is 16. Easy. Next up, our original problem, 4 cubed. Base is 4, exponent is 3, which means 4 times 4 times 4, getting us to 64. And check out how important those rules are. On that last row, we have 3, 4. We just swapped the numbers, but we get a totally different answer, 81. So you can see, the base and the exponent each have a very specific job to do. You know, the first couple of exponents are so common, they even got their own nicknames. So anytime you see an exponent of 2, like in 4 squared, you'll usually hear people say 4 squared. And this actually comes from geometry. Think about it. The area of a square with sides that are 4 units long is 4 times 4, or 4 squared.
And it's the same idea for an exponent of 3. That gets a special name too. So 4 cubed is almost always read as 4 cubed. And again, that comes straight from geometry. The volume of a cube with sides of length 4 is 4 times 4 times 4. You guessed it, 4 cubed.
Section 5. Why it's a power. So we know it's a handy shortcut, but why is it so important? Why do we use this big, important-sounding word power? Well, it's because this isn't just about saving some ink. It's a truly fundamental concept in math. And this right here is probably the biggest takeaway of the whole thing. Raising a number to a power, the official name is exponentiation, isn't just a trick with notation. It's a core arithmetic operation, just as fundamental to math as adding, subtracting, multiplying, and dividing. It's one of the main tools in the toolbox. And it's called a power for a good reason, because of the incredible speed at which these numbers grow. Exponents are a seriously powerful way to deal with the huge numbers that come from repeated multiplication. And this idea pops up everywhere, from calculating interest in your bank account to figuring out how fast populations can grow. So, we'll leave you with this final thought to chew on. We figured out what 4 cubed is, and we know what 4 squared is. So, if you apply that exact same logic, what do you think 4 to the power of 1 would be? How many times does that exponent tell the base to show up? It's a simple little question, but if you can answer it, it proves you've totally got this.